So I'm David Murray from the University of Strathclyde. We did this work with Panan IT from Serbia with Srđan Lulic, is my main collaborator. So obviously everyone knows about NILM and everyone's using deep learning now, so shouldn't have to cover that too much. There's been a lot of different approaches to deep learning. So obviously one was Jack Kelly's autoencoders and LSTM on his UK Dale dataset. A deep convolutional network approach was also taken with thousands of epochs and like 64 layers or something. There's been LSTM on red, LSTM on UK Dale, LSTM on UK Dale, and red. GRU, LSTM, CNN, all on red dataset as well. So obviously red's quite a popular dataset for testing all of these theories. But the issues with the red dataset are that it's reasonably low noise. There's not a lot of appliances going on at the same time. There's not a lot of like background on and offs things happening. And the UK Dale dataset's got more noise, obviously, but still it's quite nice because it's Jack's house. He's out a lot of the time doing research, so you know there's not a lot going on during the day, and lots of the applications also use synthetic data. And one thing we're looking at right now is no one trains on one data set and tests on a different data set. So everyone trains on red, tests on red, trains on UK Dale, tests on UK Dale, which is good for showing that your algorithm works, but it doesn't show that your algorithm works for all possible kind of approaches. So what we're asking is, can you train a network on one data set, and then can you apply it to a different data set, one where there's maybe less labeling, all that, and can that help us to reduce the amount of labeled data sets we need, so you can do unsupervised learning once you've done a bit of supervised learning on one data set to then transfer over onto other data sets, maybe from a different area or you know, different backgrounds of the homeowners. And can this transferring across data sets handle large amounts of noise, e.g. the REFIT dataset, which has tons of noise? So transferable learning, there's a bunch of different definitions for it. So we're going to talk about it in terms of you can transfer from within a data set. So if you have houses you haven't seen, so for example, if you haven't seen house 2, but you've trained on like house 5 and 6, can you transfer across to house 2, which is similar to how most people do it just now. So they might train on, say, red house 2 for 100 days and test on 20 unseen days. So that's still within the same house. So is that method learning how to do NILM, or how to do NILM on that house very well? So is it overfitting? So we're trying to build a transferable model which will do houses it hasn't seen before. Therefore, there might be appliances it hasn't seen or might trip it up. And also transferring to other data sets. So will it be able to cope with that as well? How far can we take this? Can we go from UK houses being trained on to test on American houses, which are very different, obviously, with they able to have a lot of aircon and HVAC and things like that. And yeah, would it be able to predict the appliance state and the appliance consumption? So the data sets we've looked at here are the red data set, obviously, the REFIT data set, which we made. It's great, you should use it. And the UK Dale data set. So there's a range of sampling rates here. There's 1/16 seconds, depending. And lots of different signatures. Obviously, with the REFIT houses, we have like 20 plus fridges, all sorts of things. So there's lots of data available, and it's reasonably well labeled. Like much different patterns of noise from the red to the REFIT data set, and also appliance ownage and usage varies significantly across them as well. And the appliance ages make a big difference, especially for sort of fridges and stuff. So old fridges will be less efficient than new ones. Same for most appliances, really. So what we've done with the data is we've taken the data from all the data sets, downsampled it to 1 second, forward filled it, if it needed forward filled, resampled it to 8 seconds so they all match each other, and then we've overlapped windows as our input for our networks. So we're demonstrating this on 2 networks right now. These networks are quite different. Obviously, you can see total trainable parameters are the CNN networks, a lot more, GRU networks, a lot less. So CNN, the model was designed by Surgeon, and the GRU network was designed by me. CNN's been shown to handle temporal data quite well. Obviously, it's used a lot in image processing networks, and the GRU networks are specifically designed for time series data. So, and another reason I chose it was it's less complex than LSTM, so we can reduce training times. So we've been using the same training for both networks just to make it equal. So we've not done a lot of epochs, so we didn't want to overfit horrendously. And we used a batch size of 128, and for the GRU on the fridges, we used 64, because otherwise it broke. The classification, so each network gives out a classification and an estimation of consumption. So the classification is the appliance on or off, and the estimation of power is the average power for that time window. I just want to say that accuracy should actually be in power estimation. I messed that up, sorry. And the metrics we've chosen are in alignment with some of the literature on deep neural networks that we've seen in the past. So to be able to compare it and give a sort of like good idea how the networks are doing. So the results you're about to see, there's going to be a lot of tables. I've highlighted all of the important numbers in bold. So look at the bold numbers to see what's going on. So we've got red seen to red unseen. So we are, all of the unseen houses are house 2 in the retrospective data sets, apart from UK Dale, which is whatever one Jack's house is. I think it's 1. So we've got red seen, which is going to be houses like 2, 3, 5, and 6, I think, to red unseen, sorry, ignore 2. And then red unseen, which is 2, refit seen, which is all of the houses apart from 2. Refit training to red testing means that we're going to train on the refit houses and test on the red house, and then vice versa, and then refit to UK Dale as well. So yeah, here we go. So this is our red to red. So the top one is validation, just to make sure that we're not overfitting too much on the network. So you can see that from the bold values, the important ones, just to remind everyone, that the accuracy for the power consumption, CNN's doing better in this case. GRU is better at detecting if the appliances are on. This is for the validation. And then CNN sort of does better in the estimation of power for each of the windows. When it comes to the testing on red unseen houses, you can see that they both perform equally in deciding if the appliance is on, and the GRU does a little bit better in dishwashers. There's then a sort of, GRU just did better in dishwashers in this case, and CNN did better in everything else. But the results are still quite good. And obviously this is red to red, so it's like similar houses. There's not a lot of noise, this sort of thing. So this is just our like baselines for red to red. This is our refit to refit baselines. So you can see that in the validation, they're reasonably similar. I forgot the bold, the washing machine one for the on or off. Then the accuracy is split between GRU and CNN for the power estimations. But you can see that the RMSE for GRU is better in most cases, but not by a whole lot. So they're kind of similar. For testing, again, the values are still quite good for detecting if the appliances are on or off. That's the F1 score. With the accuracy for predicting how much the appliance is actually using, CNN is tending to be better at generalizing this from house to unseen house. So this is our refit baseline then. So basically, There's smaller losses for the red data set, so you saw the F1 scores were a little bit higher because there is less going on, which is the main thing we want to talk about red. The drop in performance for washing machines and microwaves and refit was roughly about 10% F1 score and also accuracy. So there's good generalization for dishwashers across, because dishwasher is quite a like a visible appliance signature. It goes up, goes down, goes up, goes down, and it's like up to 3,000 watts. So it's pretty easy to pick it out by eye anyway. GRU is, at this time, probably less likely to transfer to a different house, especially on a different data set. CNN takes their performance hits, but the generalization makes it a more likely candidate for transferring to a different data set. So we've got our refit to red now, so I've got rid of the validation, and this is just like straight testing. So you can see, obviously, the F1 scores they've dropped off, let's be honest. So microwaves, it's gone. It's under 50%, so it's wildly guessing. Dishwasher, GRU, it's seen that dishwasher, because they're kind of similar across red and refit. And refrigerator, everyone has a fridge, and they all look the same, so it's not doing too badly. The accuracy, on the other hand, I mean, there's a drop-off from what it was previously and within the same data sets. Dishwasher accuracy, so it's detecting the dishwasher's on, kind of okay, but it's not the best when it's going to actually deciding if how much power it's using. However, I think that's something that can be addressed, and obviously the accuracy for the other appliances is doing not badly in terms of this. So as you can see, as I mentioned previously, that CNN is better at generalizing, so that's why CNN has the bulk of the accuracy scores. However, the RMSEs for GRU are a little bit better. Red to refit, so red has less noise during training and a smaller training set compared to refit. But you can see that the values are pretty good for accuracy, at least. They've not lost as much compared to the red to red and refit to refit equivalents. You may notice that there's no accuracy for fridge. That's because going from the red dataset to the refit dataset, the window size we chose meant that the network was never given an off period, an off signature for the fridge as they overlap, so the fridge was always on. Therefore, the refrigerator network for red to refit is biased to always being on, and the accuracy really suffered and wasn't very happy. We do have RMSE values, so you can see that they're for a fridge they're pretty good, but it's always assuming that the fridge is on, pretty much. So that's a window length problem, which I think we could solve, and if we were looking at it out in the field, that would be something to change to make results much better. The accuracies are bad for microwave again, but microwave is quite a small appliance, so picking it out from the aggregates tougher, but deciding if it's on or off is actually quite good values, and so is dishwasher as well for the CNN. Where are we? Refit to UK Dale. So this is one where the results for dishwasher, we don't know what happened. I think the results for dishwasher are because there are not a lot of dishwasher uses in the UK Dale dataset, so therefore if it got it wrong, it was going to get it wrong like a lot. Whereas microwave and refrigerator, yeah, they're pretty good. Refrigerator F1 score for CNN, it is very likely that that's just assuming the fridge is always on, which it is with the windows that we chose. Apart from that, the values for microwave and accuracy are quite good in this. Dishwasher and refrigerator, yeah, they're quite good. So it's showing that it is possible that you can train on one network and transfer to another. And in this case, refit is quite similar to UK Dale. They're both UK houses. We have a lot of refit data, so therefore matching up something similar to Jack's house is not too difficult. So yeah, it's good because it's showing that we can do this, and the results are not terrible, considering that we haven't seen or even considered a house similar to the UK Dale house when looking at the REFIT ones. Yeah, so this is just a sort of like backing up that. So the red's reasonable, CNN's better than GRU, like minimal performance drops apart from some appliances, obviously. CNN performs well on the REFIT one, and GRU, this is a significant performance hit on some appliances as well. So something to note is that our networks are designed so that it's sort of branching out. So it decides if the appliance is on, and then that branches back in and feeds back. So we train one part and train the other part as well simultaneously. So the idea was that if the network decides if the appliance is on or not, that will help decide what the consumption of that appliance should be. So the F1 scores throughout have been reasonable, whereas the estimation has been hit or miss in a lot of cases. Still quite good, like still not crazy though, so it could be definitely used. The power estimation for refit to red is negatively affected because the duty cycle of a lot of US appliances, specifically the fridge, is quite different from the UK. Not in a big way, but there's maybe the appliances from red are a bit older, so the duty cycle is a bit longer, and it doesn't estimate that as well. Refit to UK Dale, the performance is pretty good. Obviously, these networks have not been trained a horrendous amount of epochs. They're not the world's deepest neural networks, not that they have to be. So it's important to note that. But the performance is pretty good from Refit to UK Dale because they are very similar data sets, house styles, that sort of thing. So yeah, so we're pretty happy with where this is at so far. Generalizes pretty well in unseen houses, refit to refit. This is kind of what I've gone over a little bit. Yeah, so it's kind of showing that we don't need lots and lots of really large labeled data sets as long as we have a couple that we can then train on, then unsupervised learning, and we can maybe get away with that quite well. So we're doing more work now for the H2020 EcoBot project, which is our large-scale trial. So we've got upgraded networks from this that sort of aim for a different target variable for the neural networks, and yeah, we think it's gonna go pretty well. Other stuff that our group's working on, we're doing very low rate NILM, so that's the EcoBot project. So we're doing 1 to 10 seconds, and then we're doing 50 minutes, 30 minutes, and 60 minutes as well. And we have field trials starting in January of next year. So we've got 4 NILM methods as well. We presented one of them in Texas. I didn't, someone else did. We're also doing GSP filtering for NILM, which was also presented at the NILM Workshop 2018. We've got activity level NILM as well, which is published. Ask us about any of the papers and we'll get you links to them, no problem. And anomaly detection, and what's this? Energy measures through the bottom. That last one, I don't know that paper, but yeah. And these are just for the benefit of the stream. Those are the papers that we've also referenced in this. Thank you.